Thank you for introduction. Today I would like to talk about my recent work on how to obtain accelerating universes in the framework of string theory. This work is done in collaboration with Keiichi Maeda and his student Ryo Wakebe. First of all, I would like to explain a little bit about the motivation of this work. We are interested in the superstring theory as a theory of everything, and in order to get any evidence about this, we should try to understand, find some evidence of superstring, which is supposed to be expected to play a significant role in the quantum effect of gravity. And such a situation is typically appears in the black hole physics or physics in the early universe. And we focus on the early universe in this talk, and there are many reasons in the context of cosmology we have to have inflation. But I don't think it is necessary to explain these motivation to you, horizon problem and flatness problem. These are something to be explained within the context of string theory, if the string theory is really the theory of quantum gravity. So I want to describe some of other models of obtaining inflationary model. And the first attempt to first proposal of obtaining the inflationary model was given with a positive cosmological constant in the context of grand unified theory, where you have some cosmological constant appearing from the spontaneous breakdown of symmetry of some scalar potential, and first proposed by Guth and Sato, and then came with some modification, which is called a new inflationary model. This is the old inflationary model, and actually before that it was found that by Stravinsky that the higher order correction, such as R square, can also give a similar accelerating expansion of the universe. Without introducing artificial potential, we would like to have this behavior as a prediction of the fundamental theory, which we think is a superstring. However, if we use some effective theory of supergravity as a low energy effective theory for the superstring, it is known that there is a no-go theorem. Assuming a d-dimensional supergravity is compactified on smooth manifold without boundary, and also several reasonable assumptions, then it is shown that we cannot get accelerating expansion in this framework. But of course, there are several assumptions that are listed here. There is always a way to get rid of this no-go theorem. First, I will list some typical example of how to avoid this no-go theorem. By including additional degrees of freedom, such as d-planes, then you can find several types of inflationary model. First, proposed by Duvalier and also several other people, and also it was found if you allows the time dependence of the internal space, then you can get some accelerated expansion. And typically, this is what is called the S-brane solution in the low energy effective supergravity theory. But the problem with this proposal is that the obtained E-fold is very small, around 2 to 3. So this kind of approach cannot be used for realistic description of inflation, which requires much bigger E-folding numbers. There is some interesting solution which might be useful, but this is just some not really a realistic one. And then we went on to study higher order correction existing superstring M theory, which is typically in type 2 theory. You know, there is curvature to the force power correction in the string theory in the alpha prime. And then we find that there is a case in which we can obtain large E-folding. And the interesting feature of this kind of general solutions is the size of the internal spaces tending to become very large compared to the Planck scale. And to obtain 60 E-folding, which is a typical number we should get, numerical analysis shows that the size of the internal space is about 4,000 times the inverse of the 11-dimensional Planck scale. Then this means that that when you estimate the size, estimate the 4-dimensional Planck mass, and then you can get the 11-dimensional Planck scale should be given by something like a 600 TeV. And if this kind of result is really true, then we may achieve the energy scale of quantum gravity in near future. But to really obtain this big number of E-folding, we find that it is a little bit necessary to choose a good initial condition to achieve this large E-folding. Other approaches using
sorry, in that case, can you generate enough density perturbations with that?
Sorry?
Can you generate enough density perturbations?
This is a problem that must be addressed after you consider reheating. Because we are not using the 4-dimensional compactified theory, it is rather difficult to study that. And that will be a subject that I will be going to suggest at the end of my talk. And then also there is a proposal of using scalar field with negative kinetic term, which is called phantom cosmology. But there is no reason to use this kind of field in the context of effective string theory. And so I do not consider this kind of proposal. But you can also consider non-compact and non-compact internal manifold, or some manifold with boundary, which is typically connected with what is called the brain world cosmology. And now today, there are these approaches that I have been working on, but here today I would like to report other possibility of inflation due to higher order correction. That is, in the context of the string, heterotic string, higher order correction is known to start with second order curvature square, second order in the curvature. And this kind of solution was studied for some time, and there was some solutions studied with Gauss-Bonnet higher order correction without dilaton. But in the context of string theory, of course, dilaton has to be considered. So we started studying such a system, and here is alpha 2 is just some constant proportional to alpha prime, which is a string parameter. And then we find the system of the field equation gives the autonomous system for this kind of basically a torus type compactification of the 6th dimension. And then you can find the solution is the fixed points of this autonomous system, and the general solutions are those given by connecting these two fixed points. And there are several solutions, but we find that there is none of them gives the inflationary expansion. And this is consistent with no-go theorem, although the no-go theorem did not consider higher order corrections. Now, what we would like to propose today is, in fact, there is some field redefinition ambiguity in such an effective theory, because this kind of effective theory is determined from studying the S-matrix amplitude in the string theory, and then this can determine only the effective theory up to order alpha prime. The higher order in the alpha prime is ignored. So if you make this this kind of field redefinition, you can generate many terms up to alpha prime. Of course, there are more other higher order corrections in the alpha prime, and if you include all of them, then the theory must be should be equivalent. But because we are sure only about the alpha prime order, there is this kind of ambiguity in the theory you use. But with such many parameters, it is not so interesting to just parameterize the solution. So we impose the condition that this kind of effective action should be a Galilean type, which means that the field equation that you obtain from this action should be second order, by which we can get rid of ghosts in the system. So we impose that condition and find still we have two free parameters in the system, and using within the context of this ambiguity, we study the solution. And certainly, macroscopic objects should not depend on field redefinition. And this would be true if we include all higher order correction in alpha prime. But because we don't know such a higher order correction, we content with try to find real theory must be within this parameter. If the parameter hits the correct point, then this must be the correct solution. And if there is no interest solution within this effective theory, then this approach is end. So we have to find if really there is any interesting solution within this parameterization. Now we find with this kind of parameterization of our space-time, and then we are looking for whether it is possible to find a De Sitter type of solution. And in the four-dimensional, when compactified in 4 dimension, this is the Einstein frame you can use and you can get, and 4-dimensional metric is given by this. So in order to find a De Sitter expansion in the Einstein frame in 4 dimension, we have to have the case b equals 3c, which means that this constant b must be equal to 3 times of this coefficient. And we find there is indeed a solution with such a property. There we find only 3 kinds of solution of this type, and these are all one parameter family of De Sitter solution in this theory. So in fact, there are such a solution in this approach, and there is a possibility that you can get this De Sitter solution in this context. And this is just a possibility, and we have to further try to study what kind of consequences this should give. And we have also studied a little bit about the density perturbation when higher order corrections are present, and the result turned out that if Gauss-Bonnet term is dominant, this is the one parameterization of the system, and if the solution, if Gauss-Bonnet term is dominant, then we find that the density perturbation is too big to explain the present universe. But the higher order kinetic term is dominant compared with the Gauss-Bonnet term, then the density perturbation seems to be better, much better, almost consistent with the present observation. So what I would like to say is no-go theorem can be overcome if you include this violate some various assumptions to propose that. And various models are possible, but usually fine-tuning is necessary. And in most model, quantum correction seems to be important. In particular, higher order corrections are important in the early universe because the phenomena is at a higher energy. So we have to take care of this kind of higher order corrections. and then they can give generalized two-sister solution if field redefinition ambiguity is taken into account. And it can also produce density perturbation. Now, there are still several problems that we have to think about. That is how to finish this two-sister expansion in our solution, and also reheating must be considered, which have to be treated by including coupling to matter. In a sense, KKLT kind of setting need some maybe they may be angry if to my comment, but in my opinion, they need some complicated hoc settings, and it is rather complicated. There is one important problem with our approach, that is how to derive 4 dimension. In our approach, 4 dimension is chosen by hand, and we find a solution which describes a good 4 dimension. But there is no reason why we separate 4 from 6, and then probably what we are considering is take a good compactified theory and the approaches considered here, and then consider the higher order correction, so that as the early universe, at the higher energy, we can get the inflation using this kind of higher order corrections, and then lower energy goes to the compactified model to study the 4-dimensional theory. That is. Thank you very much.
We have time for a question. Well, I have a question, which is how did you arrange for it to be consistent to truncate to only the leading or perhaps the first 2 curvature corrections? What was it that made that possible?
This is a very important or difficult question, yes. But we simply assume that these are the most important part, and if there is any good solution within this context, this could at least show that there is a possibility that the theory can survive. If we cannot find any good solution, then this kind of approach cannot be true.
All right, so our next speaker is